Another test using the first derivative. This tells us how to find a local maximum or minimum. It doesn't say if you have a local maximum, then the derivative 0, like Fermat's theorem told us. So Fermat's theorem was what we discussed in the last section, and that was, you're already assuming you have a local extremum, and it's telling you that its derivative is 0. So the first derivative test is kind of going the other way. Suppose that you have a critical number for a continuous function f. If the derivative changes from positive to negative at that value, then f has a local maximum at c. So we saw that here. F prime changed from positive to negative at this local maximum. If f prime changes from negative to positive at c, then f has a local minimum. And actually, this is an example of that. So f changes from negative, here's f prime is this dashed straight line, to positive, and this parabola has a local minimum at the critical point, which is where the derivative is 0, which in this case is 0, 0. Here's another example of when you have a maximum. Here you see that the derivative is changing from positive to negative because the function's going from increasing to decreasing. And then there's the last case of the first derivative test, which is kind of inconclusive. If f prime is positive to the left and right of c, or negative to the left and right of c, then f has no local maximum or minimum at c. You know you don't have a maximum or minimum at that value, but so far it's not really telling you anything else about it. And we'll see that there is more information we can get from even this case. So here's an example of a function that has the derivative is 0 at when x is 0, but is negative to the left and right of that critical value. So it's not a max or min of the function f. So to an example of using the first derivative test, we want to find the local maximum of this function. Well, you find the critical values by first finding the first derivative and setting it equal to 0, and then testing around those critical values to see what the sign of the first derivative is there. So we'll test a value to the left of -1 and to the right of -1. And we see that the derivative is negative to the left of -1 and positive to the right of -1. So x equals -1 is a minimum. We see that from the graph. And likewise, we do the same with c equals 1. We test to the left of 1 and to the right of 1. We put those in the first derivative. The first derivative is positive to the left of 1 and negative to the right of 1. So I have a local maximum. One way to organize how to find the intervals on where the derivative's positive or negative is through a sign chart. So if you look at the derivative of this function, you can organize what the sign of that derivative on each interval around the zeros of the derivative, or the critical numbers, and then determine what f is doing on that interval, and then that helps you determine if you have a minimum or a maximum. So we just saw that the derivative was less than 0 to the left of -1 and greater than 0 to the right of -1. Therefore, the function is changing from decreasing to increasing at that critical value, and you have a minimum. And then you have the opposite case around value x equals 1, and you have a maximum. There's that third case with the first derivative test where it doesn't change direction on either side of the critical number. And so that's not telling you, so there's not a max or a min there, but it is telling you something relative to another characteristic of a function, and that's concavity. So for instance, if we look at this function, x minus sine x, on the interval minus pi to pi. If I take the derivative, set it equal to 0, I get the critical number at x equals 0. Now if I test on either side of x equals 0, if I plug minus pi over 2 into my derivative, I get 1. And if I plug positive pi over 2 into my derivative, I get 1. The derivative is positive on both sides of that critical number, so it's not a maximum or a minimum. But if you look at the graph of it, you can see that, again and again, these critical numbers that aren't max or mins are doing weird things with the graph. They're changing the concavity. So the concavity is the curvature of the graph. So at that value of x equals 0, the graph's not turning around, but it is changing from being curved down, sort of, at this to the left of the y-axis, and then it curves up. So at this point where the critical number is where it's changing concavity. Through these little bowls here, because another way of describing concavity is where the graph holds water. Is the graph curved such that it could hold water? So on this, to the left of the y-axis, where it's concave down, it's like a bowl upside down. It's not going to hold water. And here to the right of the y-axis, it would hold water. Sometimes concavity of a graph is very subtle, and it's hard to tell exactly if it's concave up or down just by looking at the graph. Here it's pretty obvious. Notice the tangent line. I've added the tangent line to the graph of this function. So it has a positive slope. It starts out positive. It would move for me. And then it's getting flatter. And it's horizontal at the origin itself. Then it starts increasing again as positive. So it never gets negative. It's always increasing. Another thing to notice what this means is that when the graph is concave up, notice that the tangent lines, the graph is above the tangent line. And when the graph is concave down, the graph is below the tangent line. So that's the rigorous definition of concavity. Instead of drawing bowls, you have you look at the tangent line relative to the graph. So this, again, just kind of reiterates what was said before, that this is increasing everywhere, and that critical number is showing us where it's changing concavity, not a local extremum. One thing to keep in mind, the second derivative is the derivative of the first derivative. So where the first derivative is increasing, the second derivative is greater than 0. And where the first derivative is decreasing, the second derivative is less than 0. So notice that to the left of the y-axis here, where it's concave down, that first derivative is decreasing, which means that the second derivative is less than 0. And to the right of the y-axis, where it's concave up, that first derivative, those slopes, the tangents, are increasing. So the second derivative is greater than 0. So that leads us to yet another test in this section, concavity test, which now deals with the second derivative. So if the second derivative is positive on an interval, then the graph is concave up on that interval. And if the second derivative is less than 0 on an interval, then the graph's concave down there. And the point where it changes concavity is called an inflection point. So in this case, that critical value at the origin is also an inflection point. and that's where it changes from concave down to concave up. So here's another example. Find the local extrema of this function and find the intervals of concavity and the inflection points. So to find the intervals of, first we'll start off finding the local extrema. So we'll find the critical values, the critical numbers. So we find the first derivative and set it equal to 0. Solving this equation, I get critical numbers of pi over 2 and 3 pi over 2. Then using that first derivative test, we're going to test around each of these zeros. So testing the first derivative to the left of pi over 2 gives me a negative, and to the right of pi over 2 gives me a positive. So pi over 2 is a local minimum. To the left of 3 pi over 2, I get a positive derivative, and to the right of 3 pi over 2, I get a negative derivative. So that means that 3 pi over 2 is a local maximum. So now we're going to determine the concavity and the inflection points. So we'll find the second derivative, which is this equation. And to find the inflection points, which is where it changes concavity, we'd need to set this equal to 0 and solve. And so using a trig identity here to get everything in terms of sine, and then using the quadratic formula with sine x instead of x. And I find that the inflection points occur at where the sine x is 1/2 and -1. So this interval, remember, was 0 to 2 pi. So this happens when x is pi over 6, 5 pi over 6, and 3 pi over 2. So we have to test around pi over 6. So testing to the left of pi over 6, I'm testing the second derivative now because I want to see where it's concave up and concave down. So testing 0 to pi over 6, I use pi over 12, and evaluating the second derivative there, I get a value less than 0. So f is concave down because the second derivative is less than 0 on this interval. Now I'll test a point in the next interval between pi over 6 and 5 pi over 6. So I chose pi over 3, and that was greater than 0. Therefore, f is concave up between pi over 6 and 5 pi over 6. And then between 5 pi over 6 and 3 pi over 2, I choose pi, and the second derivative is less than 0 there, so it switches to concave down again. And then 3 pi over 2 to 2 pi, I chose 11 pi over 6. It's concave down there again. So let's look at this. So the blue graph is the second derivative. The red graph, the solid red graph, is the function itself. So I'm going to turn off the first derivative for a second. So notice that it's concave down where that second derivative is less than 0. And then that red graph is concave up where my second derivative is greater than 0 above the x-axis here. Now notice that this is going to be an inflection point because my second derivative is 0 and my graph is changing from concave up to concave down. Therefore, my second derivative is going from positive to negative. So that second derivative is negative. That blue dashed graph is below the x-axis all the way until we get to 2 pi. Now notice how this flattens out here for a lot longer than here. And that's because it's actually because the first derivative is also 0 there. It's called a stationary point then. So notice that at that inflection point, when I turn this green dashed graph is my first derivative. So I'm turned that back on in this picture. So notice that the place where it changes from concave up to concave down is an inflection point. And since that's a zero of the second derivative, it's a max or min of the first derivative, since this is changing direction, changing sign. So another interpretation of an inflection point is that is where the function is changing the most rapidly. It has the most extreme rate of change there. Because remember, the first derivative is the rate of change of the function, and this is a maximum of the first derivative. So keep that in mind as another interpretation of inflection point. So here's another test for maxima and minima, the second derivative test. If you have a critical value and the second derivative is greater than 0 there, then that value is a local minimum. And if the second derivative is less than 0 there, then it's a maximum. So we have the first derivative is greater than 0 if x is not equal to 2. So that's telling me it's greater than 0 everywhere, except at x equals 2, which tells me it's probably equal to 0 there. The second derivative is greater than 0 if x is less than 2. So that's telling me that it's concave up to the left of 2. The second derivative is less than 0 if x is greater than 2. So that's telling me it's concave down to the right of 2. It has an inflection point at 2, 5, which shouldn't surprise us because we know that it changed concavity at x equals 2. The limit as x approaches infinity is 8, so that means it has a horizontal asymptote at y equals 8 to the right. And the limit as x approaches negative infinity of f of x is 0, which tells us it has a horizontal asymptote at the x-axis as we go to the left. So I think it's easiest to start with the end behavior and then fill in the gaps. So draw, tails for the end behavior. So we know that the right hand of the side of the graph is going to be going off to 8, and the left hand side of the graph at some point, and these are estimates where you would start, is going to be skimming along the x-axis as you go to the left. Then you want to fill in between. So you're given that point 2, 5. You want to draw that point. And you know that to the left of 2, 5, it's concave up. And to the right of 2, 5, it's concave down. And since that first derivative was greater than 0, it is going to be increasing everywhere. So you're not going to have a max or min that's going to turn around. So that was important to note. So that when you join these tails that you drew initially, you know that it's concave up here and concave down here. You don't need to worry about it ever changing directions and having a local max or min. Here's another example where you're given the graph of the derivative, and you need to find sketch the graph eventually by finding all these characteristics of the graph. So because this graph is the first derivative, you need to remember that it's not the graph itself. So what can you tell from the first derivative? You can tell where the function's increasing by where the first derivative's above the x-axis, and the interval where it's decreasing by seeing where it's below the x-axis. You can see local max or mins by seeing where the first derivative is crossing the x-axis so that it's changing direction on either side of a critical number. You can tell where it's concave up or concave down because remember that the second derivative tells you when it's concave up when it's greater than 0. And since the second derivative is the derivative of the first derivative, that means that where my first derivative is increasing, my second derivative has to be greater than 0. And where my first derivative is decreasing, my second derivative is going to be less than 0. So then we'll put all these together to find the graph. So f prime is positive between 1 and 6, and again from 8 to infinity. So that's where f is increasing. F prime is negative from 0 to 1 and 6 to 8. So that's where f is decreasing. The critical numbers of f prime occur the critical numbers of f occur at the zeros of f prime. So that's at 1, 6, and 8. And since f prime is going from negative to positive at 1, x equals 1 as a local minimum. Since it's going from positive to negative at 6, x equals 6 is where the local maximum occurs. And since it's going from negative to positive at 8, x equals 8 is another local minimum of f. So we've answered A and B. Now let's look at C. On what intervals is f concave upward? Well, remember, f prime is increasing where f double prime is positive. So since f prime is increasing from 0 to 2, f double prime is positive from 0 to 2, so f is concave up there. Likewise, f prime's increasing from 3 to 5, so f double prime is positive there, and f is concave up there. And then the same for 7 to infinity. Likewise, f prime's decreasing on from 2 to 3 and from 5 to 7. So f is concave down on those intervals. And then the inflection points occur at the endpoints of these intervals. So at 2, 3, 5, and 7, it's changing between concave up and concave down. So then they're giving you a point of f of 0 equals 0, so they're giving you just one point to start with, and then it's supposed to sketch the graph of f. So this is going to be in the lab as well. It's helpful to mark off along the x-axis the places where it's going to be increasing. The function will be increasing and decreasing, either on the x-axis or kind of in a field on the in the xy plane, kind of marking off, okay, my graph might appear up here and it'd be decreasing here and increasing here. You know, again, how you find best to do it. Also, plotting max and min values. So you know the x values of where they occur, but you don't know the y values. So the y values are up to you. So here's a min at x equals 1, a max when x is 6, and a min at x when x is 8. Then you want to add the inflection points, and you want to mark off where it's concave up and concave down, and it's going to be changing concavity on either side of those inflection points. So you'll know that your graph turns around at the minimum here, and it just changes curvature at the max as you pass through that inflection point to concave down, and changes curvature here again to concave up. And notice that it's increasing though from here to here. So you're going from the min to the max. You're not changing direction, you're just changing curvature, and that can be not nice to draw, as you'll see in my drawing. And then you're going to turn around at the max, and then you change concavity from concave down to concave up at this point, all the way down to the min, and then increasing again. So here's my lovely attempt. I was a math major, not an art major, and the inflection points are the ones that are kind of tricky to draw smoothly. So in this example, the inflection points, especially with my drawing, are not that subtle, but sometimes they can be hard to draw. So if you're doing it by hand, you might want to, let's say on a test, you might want to point out where the inflection point is, or that it's changing concavity there if it looks very subtle. Here's another example. Instead of being given characteristics of a graph and not knowing the equation, here we're given the equation of a graph, and we need to do the same thing, find the intervals of increase and decrease, the max and mins, concavity, and sketch it. So to find the intervals of increase and decrease, we take the first derivative and we find where it's greater than 0 and less than 0. And while we're doing that, we're finding the critical values, so we can find the max and mins with the first derivative test while we're finding where it's increasing and decreasing. So I take the derivative of this, and it's this value, or this expression, and then to see where that is greater than 0 is going to tell me the interval where f is increasing. So remember, to solve an inequality, you want to set it relative to 0. You set it as an equation. And then I'm going to factor. I'm going to treat this as a difference of two squares. And I'm going to factor. And then I'm going to set each factor equal to 0. So this factor tells me that x equals 0 and x equals minus 2 are critical values. That's when this factor is 0. And this factor is never 0. So these are my two critical values. And I'm going to test the first derivative around these values to see what it's doing. So f prime's greater than 0 to the left of minus 2 and to the right of 0. And f prime's less than 0 between minus 2 and 0. So it's increasing on this interval and it's decreasing on this interval. So now we're going to find the critical numbers. Well, we already got them. And because we know what the graph was doing on either side of those critical numbers, we determined that already. We know that f has a local maximum at minus 2. So when I evaluate the original function of that, I get the value of y equals 7. And then it had a local minimum at x equals 0. And that gives me minus 1. So now to find the intervals of concavity and the inflection points, I want to find that second derivative and set that equal to 0. Well, the second derivative is this cubic, and the only place that is 0 is when x is minus 1. And to the left of minus 1 is where the second derivative is less than 0. And to the right of minus 1 is where it's greater than 0. Therefore, minus 1, when I plug minus 1 into my original equation, minus 1, 3 is an inflection point. And it's concave down to the left of minus 1 and concave up to the right of minus 1. So to sketch that, you want to plot a few points besides just the max and min and the inflection point. So I plotted another point here at x equals 1 and at x equals minus 3. And then remember from pre-calc days, this is a polynomial. It's of degree 5. So remember what the end behavior does. So it's going to go to negative infinity for x as x goes to negative infinity, and it's going to go to positive infinity as x goes to positive infinity. So that's the end behavior of an odd degree polynomial. So you sketch that first and then kind of fill it in. So I know that it's going to go up to this local max, come through this inflection point, come down to this local min, and then connect up here again. And I'm going to try to make it change concavity at this inflection point. and instead of my horrific drawing, I let Desmos fill it in. So notice that this inflection point, the change in concavity looks very subtle here. So that's why I'm saying that doing it by hand, if it's subtle, it can be pretty tricky. So you want to mark it, inflection point. Example 6. Now you're asked to find the vertical and horizontal asymptotes in addition to all the other stuff. So remember to find the asymptotes. This doesn't have any vertical asymptotes, but to find the horizontal asymptote, we'll find the limit at infinity. And you brush off those skills. So as x goes to infinity, we can multiply by the conjugate over the conjugate. And we see that this goes to 0. So we have a horizontal asymptote at y equals 0. To find the intervals of increase and decrease in the local max and mins, I'm going to find the first derivative. And so notice the first derivative is less than 0 everywhere. And the reason that is because this term is less than 1 everywhere. And that's because notice that I have x squared plus 1 in this square root in the denominator. So this is always going to be larger than x. So this whole expression will be less than 1. So that's going to be less than 0 everywhere, which tells me my function is going to be decreasing when x is greater than 0. Now if we look at this when x is less than 0, we have to consider both cases because we have we're looking at this relative to 0. So when x is less than 0, this numerator is always negative. This is always positive, this denominator, which means this is always negative. So then I subtract 1 from that. Again, it's still always negative. So f is decreasing everywhere, to the left and right of 0. Also, right, my next graph. Also, since f prime is less than 0 everywhere, it can't equal 0 anywhere, which means that we don't have any local extrema. And then we're supposed to find the intervals of concavity. And unfortunately, this is falling off the end of the screen here. But if you find the second derivative, again, you're going to find it evaluates to this. And that's greater than 0 for all x because x, no matter what x is, when I square it, it's positive. And then this is always going to be positive. So this graph is concave up everywhere. And again, since the second derivative is never equal to 0, there are no inflection points. So then to do this, to plot this, to sketch it by hand, you want to plot a few random points from the original function. You know that it has a horizontal asymptote at the y-axis. You know that it's concave up everywhere. It's not turning around. It doesn't have any local max or mins. So if you plot several points on it, then it's you can just fairly straightforward to connect them and have the graph skim along the x-axis. This was a big, huge section, and there are a lot of problems in the homework, but summarizing, the first derivative tells us where a function's increasing or decreasing, and it will tell us where it has a maximum or a minimum, local max or min. The second derivative tells us where a function's concave up or concave down, and where it changes concavity is the inflection point, and that's where the second derivative is 0.